And it is my great pleasure to introduce our first speaker of the 2022-2023 seminar series, who is Adrián Ayala, visiting us. So he's currently a postdoc at the Institute of Instituto de Astrofísica de Andalucía, and he's working on the project Vañó, and he's an expert on star models and astronomy. So, thank you very much.
Thank you so much for the introduction. Thank you so much to everybody for coming. I would like to present here some results, some of them of my own research, and some of them about the more people activities, and all of them focus on the searching of dark matter using the information we can obtain from the observation of stars and other astrophysics observables. So first, I would like. Sorry.
Stop working. It has happened sometimes. I'm sorry. It's not working at all.
No,
We've had that. So
yeah. Let me try. Okay. No.
Maybe you could like exit the like full screen and go back.
Yeah, I think so. So yeah. Yeah. And now again. Let's try. No.
Okay.
So anyway, I think.
Yeah, we tested it was working before.
Anyway. I knew it. Okay. Screen. Okay. Yeah. Screen. No.
Otherwise, you could try
But
projecting from
it
my
seems
laptop.
it's yes.
If you would like to try
Okay.
it.
Yes.
I'll just change from here.
Yeah.
Sorry, yeah, that's not the screen one. Oh, not that. Let's see. Try again now.
Okay.
All right. Let's only we'll just keep here. This is for the recording, otherwise. It's the other side. It should be this one.
Okay.
It should be going back.
Okay. 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 Okay.
I'll maybe go back to that's it.
Thank you. Sorry for the interruption. So I would like to give you a brief overview of this talk. I would discuss what you think is light dark matter in this context. Then I would like to discuss the statistical things of this kind of dark matter. And then I would go to moving on to discuss the astrophysical constraints on axions, on dark photons. These both are kinds of light dark matter. I also would like to discuss an ongoing project about the bound we are trying to impose from Lyman-alpha on specifically on axion dark matter. And moving on, in the end, I would like to give you the conclusions conclusions of this talk. So, Alex has done a very good job, but I like to introduce myself. I studied physics in Seville University in Spain, then with a master in nuclear and particle physics. Then I moved on to astrophysics, and I got my physics and space sciences PhD by from Roma for the data and Granada University. And in this moment, I'm a postdoc research in the fields of asteroseismology and stellar models in the Andalucía Institute of Astrophysics. My fields of activity up to now, they have been astroparticles bound from stellar physics on these astroparticles, stellar models, and asteroseismology. So now, go ahead, please. One more. Oh, yeah. Okay. I will discuss the concept of light dark matter. We are dealing with a kind of dark matter candidates that they are referred in the literature as weakly interacting slither particles or WIMPs, in opposition to the WIMPs, the weakly interactive massive particles. They are low mass, typically in the electron volt kilo electron volt scale, and due to this slight mass, they can be produced inside the stars by thermal processes, as I will discuss a bit more in detail. They can interact with baryons, but very weakly, and they can escape almost free from stellar interiors, carrying away energy. And it is the most important thing for us because it is going to affect the stellar evolution. It is also going to change the stellar internal structure, and then we have some important role for asteroseismology in order to try to characterize these particles or to impose bounds on these particles model. In some theoretical frames, they can even originate both Einstein condensate, and it is important as it is going to affect the large cosmic structure. So, one of the paradigms of these particles is the axion and the axion-like particles. It is a well-known particle, and it is proposed for the first in order to solve an important problem in physics, the charge parity storm problem. It is a problem concerning the QCD, the quantum chromodynamics. And the point is that the neutron should have an electric dipole moment. And in the end, as we know, this moment is extremely low. So, we are not able to measure a significant moment, dipole moment for the neutron. So it means that the Lagrangian should not violate the charge parity symmetry. And in order to do that, we need to modify the Lagrangian and to introduce a new field where the associated quantum is called the axion. This is the gluon terms. This is a generic coupling, and this is an energy. FA is an energy scale that is important because it's going to define the couplings of axions to other particles, for instance, photons. In principle, but it depends on the model. Axion can interact with hadrons or leptons. In all cases, they can interact with photons, and this is a very important thing for us, as we will see in this seminar. In case of the classical model for the quantum thermodynamics axion, the mass and the energy scale of the axion can define a linear relation called the axion line. It is, as you can see, the mass multiplied by the energy scale should equal the pion mass multiplied by the pion energy scale. And in addition, it implies that the axion mass is proportional to a certain coupling that is proportional to the inverse of the energy scale. It has importance when you are going to impose constraints because you have two parameters related by a linear relation, as we will see in the parameter space later on. Okay, so later on, people decided that even if axion they do not exist, they had some axion-like particles that should be invoked in some theoretical scenarios. Some of them related to other theories in physics, for instance, even string theory. And these particles share with axion the properties of coupling with photons. To be a zero spin particle, they should be an additional scalar in the standard model. Not only we have place for the Higgs boson, but axion should be the second. If we are able to discover it, the second standard model scalar, and it is a massive particle. The mechanism that isn't related to the sun symmetry breaking mechanism, but we have a zero spin massive particle that could couple, it could have a coupling with the photon. It is the important thing in all the theories, the QCD axion or the axion-like particles. In addition, I would like to recall that we can consider in most of the theoretical frames the system of axion, bosons, and condensate. And it is important for the cosmological implication in order to explain some important large structured features in our lambda colder matter model. So let me go ahead. Okay, I will discuss also a exotic candidate, a new particle that should complete the standard model, and it is called the dark photon. It is a boson spin 1 particle, and in order to say something, it is the 9th modification of the standard model Lagrangian. Imagine you have the electromagnetic sector of the standard model. Here we have the familiar A, mu fields, and then we consider that there's something else, other field that could couple to this field. And with this coupling is the chi parameter, the kinetic missing parameter. We also could have a mass acquired by a technical mechanism called like Stuckelberg mechanism. It is important to recall that all these particles could produce by internal processes inside stellar plasmas. Indeed, as my collaborators and me proved, we could explain some properties of the red giant branch star using that this particle could be produced inside the degenerate core of the red giant stars. We can even detect the observational consequences in the luminosity of this star and in some parameter related to the asteroseismology, the internal pulsations that propagate inside these stars. So we propose a previous mechanism that was analog, very similar to the plasmon neutrino, oscillation, and it is a plausible mechanism to produce dark photon inside the stars. So a plethora of methods have been derived in order to try to detect these particles. Of course, we have some experiments that try to got a direct detection of these particles. We can mention some experiments that they are the practical observations, the CERN Axion Space Solar Telescope and the International Axion Observatory. They are helioscopes. They are telescopes indeed. They are devices pointing toward the sun and trying to detect these axion particles. In addition, we have also a very curious kind of experiments, the light shining through the walls experiments at Tesi in Germany. We have also the most exotic of them is a kind of mirror built like a parabolic antenna that could concentrate the decays of dark photon. So it's called the Funk experiment in I think in Karlsruhe, in Germany. And we have underground labs. They were built for other particles, for instance, for neutrino, like for instance the ongoing Viñuales experiment. But they some of these underground labs were devoted to light particles in general. Even one of them, the Xenon 1T experiment, claimed a possible detection in the 2020 a couple of years ago, but it's under discussion. It's not so evident that they detected for the first dark matter. So here I will explain just very briefly the CERN Axion Solar Telescope. So it's not a joke, it's that indeed Frank Wilczek proposed the name of the particle in the 70s because after a famous shock. Because in his opinion, axion was the perfect solution for a very dirty problem in nuclear physics. So people used to make this kind of jokes. As you can see, we have this helioscope pointing toward the sun, and we have this degree of freedom. See, the interesting thing is that we can observe the sun at the dusk and at the sunrise. They are the two extremes of this helioscope. And the interesting thing is that this is a magnet with a very strong magnetic field. The point is that in the presence of this magnetic field, the axion can be could be converted into photons. And these photons could be detected as an excess of X-ray photons. It's undetected. Notice that it is close. So the important point is that axions that can go through a blocking wall can be converted into photons here inside with the presence of a magnetic field. And then you can detect an X-ray excess. This is the experimental devices in this case. So, it doesn't work.
It doesn't work. Sorry, I can. Well,
okay.
I don't do it.
Okay.
Yes.
So it is more the future experiment. The International Axion Observatory is pretty much similar to the CAS experiment, but more an upgrade of the previous technology. And this is a very interesting experiment to try to detect this kind of action. It is the so-called light shining through the walls. Here we have an intense laser beam. You have a blocking wall where, of course, light could not propagate through, but you can apply here a strong magnetic field. The point is that the photons, the two virtual photons, can interact and can produce an axion, a weakly interacting particle. This axion can go to the wall. And then, if you apply again a second magnetic field, you can convert back the action into photons. And you can detect this. So because of that, this kind of experiment are supported, light shining through the world. Okay. Okay. Because I bothered you with all this about the physical particle physics experiments, because in my views we have now the ideas to understand what axions are doing inside the stars and how we could eventually detect this particle. So all the experiments I explained before are related to direct detection. We are going now to discuss the indirect detection. That means to try to compare our standard ideas about the way the stars evolve with the modified stellar evolution or stellar structure if we introduce these particles inside the stellar plasma. And as you will see, there are a lot of difference, and some of them enable us to impose constraints. So I will discuss in this talk some observables from main sequence and evolved stars, from observables from stellar populations like globular clusters, observables from coming from compact objects like neutron stars, especially the X-ray spectra, or even in the real of asteroseismology, the white dwarf pulsation. And I would like to have some words for a new kind of exotic project. This is the observables I will focus on, and they are mostly from the stellar astrophysics. Of course, there are some kind of indirect evidence or constraints we can try to impose from galaxies and cosmology. And I will mention in the end the Lyman data as a working in progress. But some people is working evidence from the accretion in black hole, galaxy nuclei, galaxy cluster, and galaxy satellite system. So all this system could give us some evidence, some hints, or even and eventually they enable us to impose constraints. Okay. The strong points when we are going to consider the stars, the WIS, axion and dark photon, can be produced by thermal processes. Thermal processes are, if you consider very dense and hot stellar plasma, typically with high densities and strong couplings, they are the ideal condition to expect that the common matter can produce this kind of axion-like particles in many theoretical scenarios. For instance, we can consider the Lyman-alpha effect, that it is the interaction of two photons inside a stellar medium in order to produce an axion. It's the same that I have shown you before with the light shining through the world experiment. But in this case, we have two photons inside a stellar plasma that could be interact, and they can produce an axion. This is the Lyman-alpha effect. We have also the Bremsstrahlung. When you have media with a high electron density, you can expect that the electrons can suffer a kind of Bremsstrahlung, but instead of producing X-ray photons, they can even produce axions. And we have also pair annihilation processes, like the particle-antiparticle, that in some scenarios, low probability channel of this process is the final production of axions instead of two photons. So all these processes could take place inside the stellar plasma. And this is very important, we can produce particles that can be considered an effective energy sink. They are produced and they escape almost free from the stellar interior. Then they carry away energy. But it's in a very similar way like neutrinos in the supernovae models. Then, because of its energy that is carried away, the stellar structure and the stellar evolution will be modified. So, let's discuss a bit what has been done with axions in case of the solar light experiment. I previously discussed the CATS experiment, and I will show you the limits this experiment has obtained. Of course, the future IAA observatory will try to improve the bounds that CATS was able to impose. And all these experiments, in the end, are trying to detect an X-ray photon in this kind of magnet that should be explained by the fact that the axions that were produced in the sun, they are pointing toward the sun, are converted into an X-ray excess. Let's discuss a bit the way this axion can be produced inside the sun. I discussed the Primakov effect. I said to you that it was the two photon interaction, and let's focus on the formula. We have here the temperature up to the 7, and in the denominator we have the density, and we have here a coupling constant. This constant measures how intense is the interaction between axion and photon. It is completely a free parameter. We have a nice Lagrangian, we have a modification to explain things in particle physics. We can propose a model, and it's a free parameter. Indeed, the range of variation is really broad. So the important point is that Primakov effect, the higher the temperature is, the most important becomes. Because of that, we can expect that in the hot stellar interior, this rate is important. We have right now a limit on this constant by the CATS experiment. This is the 0.6 times 10 to minus 10. The units should be giga electron volt to minus 1. This is the units you use to measure the coupling constant. So we have a limit, as you can see, it's really small, because this limit was reached by CATS in 2017. A couple of years later, that I proposed the most stringent bound up to the date. Go ahead, please. So, as you can check, we are going more in detail with the stellar interiors and the stellar physics. So we can constrain axion not only by this kind of direct experiment, that observation. We can try to look into the stellar models, and we can try to see what happens when you introduce these particles. For instance, if you consider some observables related to the sound profile differences, you cannot verify differences when you consider different coupling constants on the, for the Primakov effect between the axion and the photon. Yeah, here sorry, because it's very small. Can you see it? Well, so the dashed lines and the continuous line correspond to two solar composition models, and these are the observational. In this sense, this is the inversion, the mathematical technique called like inversion errors. This is the model error. You can see it's difficult here to be able to impose constraints, because at least in this region, this is the sun from the center to the outer shell. So as you can see, when we are showing here, this is the sound profile. It's a parameter measuring the sound velocity inside the sun. For small radius, you can see that we can discriminate, at least in case of one of the solar composition models, a bit this coupling constant. This is the authors did something similar with the hidden photon particles. But the important thing is that I can say that it's a very complete study because they use not only the cosmology, they use all two neutrino detailed measurement from Boretsino experiments, and they were able to derive constants on the coupling between the axion and the photon in the sun for the first time in 2015. So then, as a way to resume, to summarize, primary cause, increasing temperature, and we can expect that not only in main sequence star, but going across the Hertzsprung-Russell diagram, where the internal temperature are going to rise, we can hope that this effect, this primary cause effect, is going to get more and more important. And that's the important thing, that we can use the helium burning globular cluster star, the stars that are burning helium in the convective cores as a probe of the action, by means of trying to looking into the primary cause effect. Let me discuss how my collaborators and I did that. So the point is that if you consider the primary cause effect, remember we are considering an energy. So the stars are losing energy from their internal cores. So the point is that an helium burning star is losing energy faster than a standard helium burning star. It should last a shorter time in the helium burning phase. So the lifetime, the helium burning should be shorter compared with the time that the same star lasts in the upper red giant branch region, where we do not expect to have a primary cause effect. Why? Because in that case, in the red giant branch, we have degeneracy, and primary cause effect is strongly hampered by degeneracy. So this ratio should be more linear and should decrease more and more when we consider a higher primary cause effect. So, okay, that's good, that's a model, but how can we measure that? Okay, we can put in correspondence the time, the lifetime with the number of the stars we can observe. See here, this is the horizontal branch star, and this is the upper giant branch stars. So imagine, here, these stars are producing axions, they are cooling, they have an extra cooling process. They are getting, in order to compensate this cooling, they need to increase the nuclear reaction rate. They need to go faster through this region. So the number of stars in this horizontal branch should decrease when we compare this. This is a well-known parameter in observational stellar physics called the R parameter. Was initially proposed to measure the helium you have in a globular cluster, because it's strongly dependent. It is strongly dependent on the helium you have in the end. So what we did, we were able to establish or to derive a nice, very simple formula between the coupling constant between the axion and the gamma, the photon, depending on the initial helium of a globular cluster and the R parameter. This parameter you can measure. You have a lot of globular clusters, but you can distinguish a kind of star. Other kind you can count, divide, and you have the R parameter. So it's very simple in order to impose constraints. Go ahead, please. And what we did, indeed, do you remember this number? This is the CAS limit. I will explain why it's here in this part of this diagram. What we did in the end was to play with the uncertainties in the helium that we have in a sample of globular cluster where we know the R parameters. So we can, this line corresponds to the formula I had showed you before. And this is the observational limits for helium, 1 sigma and 2 sigma. And this is the observational limits for the R parameter. And we consider the good fit formula I have shown to you before. So we can derive the limit simply going to the upper limit of the helium and the upper limit on the R parameter. So this number is the bound we derive. It's pretty much the same 2 or 3 years ago CAS was able to reach. So in this case, an astrophysical observation paves the way for a bound that was obtained later on. So in this case, it is very useful because you can guide the theoreticians or the experimental physicists, and you can to discover or you can recommend which region of the parameter space you can explore more fruitfully. Go ahead, please. So, I will discuss a very nice research that was done with in case of the white dwarf. In this case, different stars have different scenarios. You cannot expect to have the same processes. In this case, the high electron density favors that the white dwarf inside the white dwarf, you can expect that the axion can interact with electrons. You have a lot of electrons, a very rich environment, and there's a process that depends on another kind of coupling. Which is the best observable we can try to use in that case? Okay, the white dwarfs are cooling. They are not shining more. They are, of course, a bit in the ultraviolet, but they are cooling. They are dead stars. So in that cooling process, you can expect that it is going to going faster when you consider the emission of axions. In that case, taking into account that what you are pulsate, you can expect that the pulsation drift is going to vary when you consider an additional cooling due to axions. It's a very simple image. You consider you are the white dwarf is pulsating, it's cooling, it's losing energy, so it's going to go slow down in their gravity mode pulsation. This is a kind of mode that the white dwarf can excite. So if you consider the axion production and emission, you are going to have an additional cooling and the period drift, and it sets in the period drift. The period is going to vary faster with time. So it is proportional to the cooling, that is proportional. This period drift is observable proportional to the coupling constant, and you can even derive a formula between the axion mass and the axion electron coupling, a relation, and then you can use that to constrain, in that case, the axion mass. Go ahead, please.
10 minutes more or less.
Yes.
Yeah, sorry. Yeah,
Yes.
sorry.
So, sorry? Yeah, sorry, yes. It's my mistake. It was a typo. A beta is an angle, a generical angle, pretty much similar to some the neutrino mix angles and so on. It's a parameter. Okay, but go ahead, please. Then, taking into account the most precise measurement of this period drift, you are able, taking into account again the uncertainty, to derive a value for the axion mass. This is the most recent estimation in 2021 by Kepler. So moving on, I will
In 10 minutes.
10 minutes, okay. Okay. So I would like to discuss these neutron stars, but I think I can go ahead because I have no more.
Yeah, just
Sorry.
how much you want here?
Yes. I prefer to discuss the dark photons hints that we obtain using the asteroseismic observable. It's a work I accomplished with Professor Lopez and other collaborators, and we used a mechanism, theoretical mechanism that could justify the presence of dark photons inside stars, the plasmon decay mechanism. The formula is not that complicated, but remember that the dark photon, it has a coupling with the photon, and it has a mass, 2 parameters. It's a very nice model. It's the same, almost everywhere. You have a model, you have some kind of parameters, you have to be clever enough to show an environment to propose where it should have some relevance, and you are able to constrain particles. So we have, this is the red formula for kind of excitation of the plasma called the longitudinal, the L mode. It is a resonant formula where you expect that it is going to be really important when the mass of the dark photon is close to the plasma frequency divided by temperature. The mass of the dark photon divided by internal temperature, is similar to that. If you make the derivation, you obtain in the end a direct delta, and you have a kind of resonance. So go ahead, please. So the point is, again, in case of the red giant branch, dark photons are an effective energy sink. In that case, they can be produced in the relative degenerate mode. In that case, the degeneracy is not for us a problem, like it was in case of axion, because the dark photons are produced by plasmon oscillation, a kind of mechanism enhanced when that it is enhanced when you have degeneration. In that case, imagine if you remember a bit of the, you know, some a bit in detail the physics of the red giant branch. You have a radiative core, and you have a convective structure, convective envelope. This kind of dark photon production and energy loss is going to affect the internal structure of the stars, and it is also going to increase the total amount of helium you can produce inside the core of the star. So we expect that luminosity at the higher luminosity region and the extension of the convective structure and the asteroseismic, the pulsation of the star are going to be modified. We make a full set of simulations. Go ahead, please. And this is some results obtained with meta codes. As you can see here, this is the region known as the RGB band. It's a region where the convective envelope reaches the internal region of the star, and the most important is the mass fraction of the convective envelope. The less bright is the star, because you are increasing the amount of fresh hydrogen. You are make some kind of dilution of the heavier nuclei, and then you are going to hamper or to cut a bit the nuclear reaction rates. So if you have a more efficient cooling process by means of this dark photon, as you can see, the band is less and less bright. It's a result in the model. And it is all in correspondence with what we expected from the our ideas about the stellar evolution and the role played by these particles. Go ahead, please. So as you can see, in other region of the red giant branch star, the luminosity increase. This is the region of the phase called light peak, previous to the helium burning in a low mass star. And as it depends on the helium content, the most important is the dark photon effect, that it is driven by the coupling constant and the mass. When you have a heavier model and a coupling constant more and more important, the energy carried away by the particle are more and more important, then you can here verify that the luminosity is going to increase. Let me recall that these variations are perfectly detectable with the modern photometry technique. So we can obtain very strong constraints on this. And I will discuss the astrophysical observables in the red giant branch. The average large separation is related to the way the internal structure of the red giant branch is condensed. It's a parameter that basically measures when you have the pressure modes, acoustic pressure modes, you can verify that you have a regular pattern in this spectrum. So this is this pattern, the value of this splitting between the power spectrum lines is the average, the large separation. So we verify that these observables increase when we introduce the dark photons in the model in a way that it is completely detectable. Go ahead. We have here the dash and continuous colored line. They are the theoretical model, and the red one are the observation. It's determination of red giant branch at the bump phase. The first phase I discussed, not the tip, when the maximum luminosity is reached, but the bump phase. As you can see, this panel corresponds to 300 mass in electron volt for the dark photon. This is 500 mass for the dark photon, 700 and 900. And the red line corresponds to a reference model without dark photon. You can see that that's an offset with respect to the observation, but we can take that under control. It's only a question of the MESA mode, the MESA code version, and the fact that the authors that derive the observational line, they consider different metallicities. For simplicity, we just consider a value of metallicity in our grid. But you can see that the red line is here relatively close to the observation. When you introduce heavier more coupled to photon, dark photon, you have this offset forward higher large separation values. And it is something you can verify with observation. And indeed, we were able to, go ahead please, to exclude a number of models. All these models are excluded in our study. Let me go back for a moment. Let me explain just a technical detail. You can see that we have here dashed lines. Okay, the dashed lines correspond to the inclusion of core overshooting, that it is an absorbed plane the same role that the dark photons. They are also increasing the average large separation. But taking into account that the two effects compete, they go in the same direction. We can even, with taking that into account, exclude some dark photon models, because even if we consider a very slight overshooting, we can exclude some values of masses and dark photon coupling constants. Go ahead, please. Okay. So I can here discuss very briefly the constants you have from task and observation in case of axion. for the mass and the coupling, you can see here this nice line for the QCD case. And you can see that here is the bound I derived. It's pretty much the same that the lower bound does. There's plenty of room in the bottom to fill this kind of flux in the picture. Go ahead, please. We have the same with the photon. We contributed filling a bit this region. Okay, most of the ongoing experiments are going to show the relatively slight low masses, but with stellar observable, you are here, and we are able to impose constraints in this region. Okay, I'm very as way previous to the conclusion. I will mention that Axions condensates could also have an influence on the cosmological structures, taking into account that the Lyman-alpha forest spectrum is sensible to this kind of structures. Some models preclude the formation of the hydrogen mass anisotrope inhomogeneities when we consider some values of the mass of the axion and the coupling to photons. So this is an additional way to impose constraint that I'm trying to explore in next future. Go ahead. For that, I will try to improve, to do a line simulation of the power spectrum of Lyman line, taking into account physical input that matter models input. Go ahead, please. So I clear discussion in conclusion. I would like to recall two important things. First, that this kind of astrophysics can detect things of our matter in stellar observables. Not only, of course, we can impose constraint, but even we can detect some kind of stress or tension in the models that could be alleviated introducing dark matter. So it should be a way to prove the existence or not of dark matter, and that asteroseismology has a great potential for the dark matter model as far as it is able to pierce inside the stellar structure and to give us precise information about the stellar structure. We can verify these changes in the asteroseismic parameters when we introduce dark matter in the models, and we can try to look for them in the in some service observations. So go ahead. This is some of my work in progress right now. Thank you so much for attending the seminar. I'm looking forward for your questions.
Thanks very much for the nice talk. Yeah, due to the technical difficulties, it got a bit later, but we still have time for some questions. So who would like to go first?
In options, not really. There are photons.
Before that, that's last slide.
Okay. Yeah, I didn't discuss about
What?
oh, what part?
No. Yeah, this is what that kind of start.
This is yeah. Helium burning start. Sorry.
Okay. Very much this start like very strong magnetic field. And therefore it's very strong field for something like the space that you have now. Telescopes. You have also the Primakov emission and inverse Primakov emission, which somehow.
But in helium burning, you mean? Okay, because
it's red giant, I mean, red giant. And I will check out one of that. If it is okay, then you are prepared to improve the model.
Yes, but somehow you need to have, if you are looking for a signal due to Primakov effect and signal in the spectrum, you need first that action are there, were there. So you need to produce them. And the point for the red giant is the degeneracy of the medium, because the Primakov effect is strongly suppressed. But anyway, you can expect to constrain. Yeah, you could have perhaps brainstorm processes, or you could brainstorm for brainstorm. You could try to impose constraints, but it is not exactly the same mechanism. Yes, they did that. Even with the sun. So yes, all the limits you can derive are up to conservative. So if you consider additional channels, of course, these numbers are going to vary. But the point is, you very often choose the most suitable, the most favorable process. But then, if you have a process that it is an orders of magnitude more probable than the other, you are going to focus on this.
If you enjoyed the video, like and subscribe.